Assalamu alaikum and welcome back to the lecture number 4. In this lecture we are going to discuss the remaining parts of the operations on signals, and we discuss some part of the elementary signals, which is a new topic. So you all know in this part of the course we are dealing with the time domain signals, and you understand the independent variable, which is time, can have two different versions, that is continuous one and the discrete one. So if the independent variable is continuous, then we call such signal as continuous time signal, and if the discrete if the time variable has if the independent variable, which is time, has the discrete values, then we call such a system such a signal as discrete time signal, right? So previously we have done the operations on the dependent variable, which is x of t or x of n, and for the case of independent variable, which is t or n, we have performed two operations, namely the time shifting and the time scaling. So today we are going to discuss about the third and final topic of the operations on the independent variable, which is time reversal. So time reversal is defined as the reflection of a signal about the vertical axis. So for the case of continuous time signal, we have x of t, our signal, and we obtain the signal y of t by replacing t with minus t, that is y of t equals to x of minus t, and we call y of t as the reflected version of x of t. Similarly, for the case of discrete time signal, we obtain y of t by replacing n with minus n, so we get y of n equals to x of minus n, and it is clearly from minus sign that the obtained signal will be the time reversal or time reflected version of the input signal, right? So shown here are two examples. One example of the continuous time signal. Here you see that in part A we have a signal x of t, and in part B we obtain its time reversal form, right? So how do we obtain the time reversal version of the original signal? So if we put a mirror here, right, and if we look from this side, okay, so we will find the reflection of this signal on this side, right, on the negative side. So if I look at into the mirror, so you can see the reflected version of this signal, right, that is from 0 up to 5, it will be from 0 up to minus 5. Again, if I put here mirror here, and if I look from this side, then the signal, which is from minus 2 up to 0, this part, it will be shown here, right? So which is this one. Thus the time reflected version of this signal x of t will be this one. Okay, so similar arguments apply for the case of the discrete time signal. So for example, we have a discrete time signal defined by x of n, which is equal to 1 for n equals to 1. It has value of minus 1 when n equals to minus 1, and 0 when either n is 0 or absolute of n is greater than 1. So that means if we go in the negative direction, that means if n is minus 1, if n is greater than minus 1, or if it is greater than plus 1, for all such values it will be 0. So that means we have only two non-zero samples. So I hope you understand this description of the signal, right? So that's quite straightforward. You say 1 when n equals to 1, minus 1 when n equals to minus 1, and 0 for this range. It means when n equals to 0, this is 0, and when n absolute is greater than 1. So n absolute greater than 1 means whether n is minus 2, minus 3, minus 4, and so on, or n is plus 2, plus 3, plus 4, and so on. For all such values, it will be 0. So let's to find y of n, first let's plot the signal x of n. So x of n will be something like this, your independent variable n, right? This is the n axis, and the values of the signal will be along this axis, right? So it says that when n equals to 1, we have value equals to 1, so it will be 1, okay, at n equals to 1, and it is again minus 1 when n equals to minus 1. So this is 0. At this point n will be 0, at this point n equals to 1, at this point n equals to 2, and so on. So at this point we have n equals to minus 1, right? So n equals to minus 1, and also value of the signal equals to minus 1, right? So looking at this definition, n equals to 0, signal is 0. So here I have circled, made a small circle, so that shows that it has value of 0. Again at 2, right? So this is 2, this is 3, right? So on, and again because it says it is 0, right? So based on the definition, which is the signal is defined here, so based on this definition we can easily plot the signal. This is the point where n equals to minus 2. At this point it will be minus 3, right? At this point it will be minus 4. So we can say that this signal equals to 0 for all, right? So this dot means this is 0. So it has only two non-zero values, which is at n equals to 1 and n equals to minus 1. Now to obtain the time reversal of this signal, so if you put a mirror here, right? So this side, right, from this side, if we put a mirror and looking at this side, so replica of this side, it will be produced here, right? So if we look at this one, so at 0 it has value of 0. At 1, now the replica will be made here, and that is the location minus 1. So at minus 1 it will have value of 1. Again this is 2, so replica will be formed here, so our image will be formed here, so that will be 0. So that means this signal will be 0, right? The reflect for 2, for 3, and so on, right? Again if we put mirror here and look in this, right? So the mirror of the image of this side will be formed to the positive side, right? So if we look into the mirror, then at 0 it is 0, at minus 1 it is minus 1, so now the minus 1 point will become plus 1. So now it is 1 at it is signal is minus 1 at n equals to 1, and all for all the rest of values it is 0. So we say it is 0, 0, 0, and so on, right? So this is the signal you obtain, and we represent it by x of minus n. Okay, now you have two signals, x of n and x of minus n, and you know that y of n equals to summation of the 2, right? So you understand. And now this second operation, this is operation on the dependent variable, right? So you have studied this, that the different operation we can perform on the dependent variable are the summation or subtraction of the signal, multiplication of the signal, integration, differentiation, and so on, right? So this operation is the operation on the dependent variable, whereas this operation, which is reflection, is operation on the independent variable, right? So first we obtain, to sum the two signal, we need the two signals. So we already have the first one signal, which is this one, and to obtain the second signal we perform operation on the independent variable, because it is mentioned that the this signal is basically the reflected version of this signal. So we have been given this signal mathematically defined here, and then we plotted it here. So after plotting this, we find this signal, which is the time reflection of the original signal. So this is the plot for that, and the resulting signal y of n equals to summation of the two signals. So in order to either sum them, or if you have two signal whose product we need to find, then for either summation or product or multiplication, we multiply or sum the corresponding values. So in this case we need to sum them, so we will add the corresponding value. So again you can see that from minus infinity up to -2, this signal is 0 and this signal is also 0. So that means y of n, right, it will be equal to 0, and we can write it like for this is equal to 0 when n is less than how much? -1, right? So less than -1, because this is discrete, so less than -1 cannot be -1.5 or -1.7 or so on. Less than -1 means -2, -3, -1. So if we sum this part from -2 up to -infinity, and here also -2 up to -infinity, because both are 0, so the summation will be 0. At n equals to 1, right? So at n equals to 1, this signal is 1, whereas this signal is -1. So again it will be 0. So we say y of n equals to 0 for n equals to -1. Okay, at 0 this signal is 0 and this is also 0, so summation of the two signal will result into 0. So again we have this signal equal to 0 when n equals to 0. So the third point is -1. At -1 this signal is sorry, not -1, +1. At +1 this signal is -1, and this signal has amplitude of +1. So adding the two will result into 0. So again this is a 0. So that means the resulting signal y of n will be 0 for all values of, and this is equal to 0 when n equals to 1. And for other values, that is n equals to 2 and up to infinity, this signal is 0 and this signal is also 0. So that means this is equal to 0 for n is greater than 1. So that means, because for all values this is 0, so we can say y of n equals to 0. So I hope it gives you the understanding how we reflect the signal, right? How we do the time reversal and how we do the addition, right? So how we will perform the combined operations. For example, we have the input signal x of a t minus b. So you understand this is a continuous time signal because t is here. So similar logic or similar arguments apply for the case of the discrete time signal. So if you look at this one, basically we are performing two operations, right? So A is multiplied here, so that means we are scaling the independent variable, and B is here, so that means B is showing the shift. So how we will proceed with this type of problems where we are given more than one operations on the independent variable at a time, right? So there are two ways we can go, and the preferred one is this one, right? The first one, and that is we shift. Okay, we perform, because the shift operation has the precedence, right? So we perform first shift, right? And after shifting the signal, we perform the scaling operation, right? So in this case, it's scaled by version of by a factor of a. So that means we shift the signal. We have original signal x of t, right? So we have the original signal x of t. First of all, we will shift the signal by amount of b, and after shifting the signal by amount of b, then we will scale the resulting signal by the amount of by the scale of a. So this is how we obtain, right? And you understand the shifting. So if b is positive, that means the shifted version will be the delayed version, because we will shift it to the right side. And if b is negative, in that case the signal will be shifted to the left side, or we can also call such a version as the advanced version of x of t, right? The second way we can do is to time scale first. So first we scale the signal by a factor of a, and then to shift the signal we have to shift it not by b, but it should be shifted by the value of b by a, right? So I think that's why I will prefer that you should opt for the first method. That's quite straightforward. You keep in mind that uh, uh, shifting has the precedence. So if we have more than one operation at a time, that means we will shift the signal first, and then we will perform the resulting operation, that is scaling or okay. So these are the examples of the signal that for practice, right? So this is the numerical example for the practice, and you are given a signal that is defined here, graphically defined, right? So this signal has a value of 1 from 0 up to 1, and it has a value from 1 up to 2. This is a decreasing value, and at 2 it comes to 0. So this signal is defined only for 0 up to 2. That means from 0 up to 2 it has some value. Beyond 2 its value is 0, and also before 0 means 0 up to infinity, it has a value of 0. So you have to perform the different operations. I hope you will practice by yourself. That is, you do the shift here, you do the shift and reflection here, and you're doing the scaling here, and here you are again doing two operations, that is the shift and the scaling. Okay, so this for example 1. I want you to go through it and do it by yourself. Even if you get a wrong answer, it's fine, but you must try yourself so that you learn it. Okay, when you do, you learn. When you copy, you just memorize maybe. So because these are very basic things, and as far as signal and system is concerned, so most of the mathematics you require, that is up to the FSC level, right? Like we can say more than 95% of the math required in this course will be up to the FSC level. That includes just differentiation, simple differentiation, not complex one, and simple integration and summation and those kind of, or the very basic arithmetic, right? So the second example shown here is a signal, that is x1 of t is graphically shown here, and this this is the x2 of t, and all you need to do is that you subtract the x2 of t from x1 of t, right? So the easy way to make subtraction is the get the minus x of 2t, right? So once you get minus x, this is x of 2t, so how can you find minus x of 2t? Once you find that, you add the two signals, right? So you get the resulting signal, which is x1 of t minus x2 of t. Again, these are some of the examples I want you to go through, right? So again, it has some I have to say the operations on independent variable. So this is the example for the continuous time case. It's a little tough, not very difficult, but tough because it has many segments. This is minus 2 to up to minus 1, then again you have this, and again this one and this one. So I hope that will help you a lot in clearing the concepts of the operations, right? So again, this one is an example of the discrete time signal that is defined for only this part. After that, the signal is right, so that's minus 4. From minus 5 onwards, the signal is 0, and again from plus 4 onwards, the signal is 0. So values are mentioned on the each sample. For example, here it has a value at minus 4, the signal has a value of minus 1. At minus 3, it has value of minus 1 by 2. At minus 2, this, and so on. So I hope they will be quite straightforward. You must go through them, and once you go through them, I think that will help you a lot in developing concepts. So to make a concept a bit more clear, let's take a comparison example for the operation on independent and dependent variable. So let's plot a signal. For example, we have signal this one, okay, and it has a value of, for example, okay, we take a pulse, okay. So for example, it has amplitude of +2 and amplitude of -2, okay. And for example, this is 2 and this is 4, okay, and this is your t-axis. So I think you can take a similar example on the you can make by yourself for the case of discrete time signals. So this is your x of t, right? And now we just going to perform, for example, just operation of the, so for example, I say y1 of t, this is equals to for example, we take the scaling factor of -2, so this is equal to this, okay. So y1 of t equals to -2 x of t. Okay, so from this -2, because we are doing no operation here, so you understand this is basically the operation performed on the dependent variable, right? The signal is defined right as this one as shown here. So that means from 0 up to 2, this signal has amplitude of 2, and from 2 up to 4, this signal has amplitude of -2. Now what will happen if we perform this operation? So clearly we are performing operation on the dependent variable, so nothing will happen along this, right? You understand that if we perform some operation, so it will be on the t, the independent variable, then it will be either compressed, or the signal will be shifted, or it will be reflected. These are the three operations we perform. So because nothing is involved here, so it will stay as it is. Now to scale it by a factor of -2, that you understand, if I scale it by a 2, so what will happen? It will be double, right? So like it is, this value is 2, so if I scale it by a factor of 2 it will become 4, and this value is minus 2, so if I scale it by a factor of 2 it will become minus 4. But because there is a minus sign involved here, so that means if you multiply anything with minus 2, what will happen, right? So in general you understand, if I multiply minus 2 with plus 2, what will happen? The result will be minus 4. Similarly, if I multiply minus 2 with minus 2, it will result into uh, plus 4, right? So if I multiply minus 2 with this signal, the result will be, okay, let's plot here. So if it's easy for you, you can do like this, or you can also plot the scaling factor, this one, right? If you want, you can also plot this one. So if it is easy for you in this way or this way, okay, so this is for example t, and this is your okay, so this is the signal, right, constant signal. This is your minus 2, right? So this minus 2 is because it's a constant, so that means it exists on all values of t. That means this is minus 2 from minus infinity up to infinity. So what will happen if I multiply the two signal, right? So I hope you understand that from 0 up to minus infinity, this signal is minus 2, whereas this one is from 0 up to minus infinity it is 0. So anything multiplied by 0, it will result into 0. So that's minus 2 multiplied by 0, it will result into 0. So you get 0. Okay, then from 0 up to 2, this signal is 2, right? From 0 up to 2, this signal is 2, so that means 2 multiplied by minus 2, it will result into minus 4. So that means the value from 0 up to 2 will be minus 4. Why? Because it's from 0 to 2 is, this one is 2, and this one is 0 up to 2 is minus 2. So minus 2 multiplied by minus 2, it will result minus 2 into plus 2, it will result into minus 4. So that means we have this thing, right? So minus 4 again. Okay, now from 2 up to 4, this signal is minus 2, and from 2 up to 4, right, this signal is minus 2. So minus 2 multiplied by minus 2, it will result into plus 4. So that means we get something like this, okay, up to 4. So this is 4, right? So we get minus 4 and plus 4. Okay, so from 4 onwards, you understand, this signal is 0, but this signal is minus 2. So minus 2 multiplied by 0, so that will stay 0. So I hope that gives you idea that this signal, the resulting signal, will stay 0 up to infinity, right? So it is also 0 up to minus infinity. From 0, right, this is your 0, this is 2, and this is 4. From 0 to 2, it will be minus 4. From 2 to 4, it will be plus 4, right? So again, by just using your common sense, if you scale a signal by a factor of minus 2, so that means there will be inversion and there will be scaling. So because this is in the original signal, this is plus 2, now because of the minus sign, it will become minus, and because you're scaling it by a factor of 2, so scaling the 2 by a factor of 2 will result into minus 4. Again, for this part, you understand this is a piecewise signal, right? So we define it at different intervals of time. So from 0 to 2, it has value of 2, and from 2 to 4, it has value of 4. So again, right? So I hope this gives you the idea of how we scale the signal, right? Again, we take another example. We perform on the same signal, for example y of t, and this is equal to for example this is equal to x of minus 2t, right? So what does that mean? That means we are doing nothing here, right? Neither there is the addition of two signals or integration or differentiation or scaling or anything. So that means we are not performing no operation on the dependent variable, right? So what we are doing, we are scaling the signal by a factor of 2, and minus sign indicates we are also reflecting it, right? So that means along this axis nothing is going to happen, okay, but along this axis, t axis, two things are happening. One is the scaling of the signal by a factor of 2, and the other is reflection, right? So let's do the scaling first. Okay, we can do either operation first because both operations are similar. The priority or precedence is for the shift operation, which is not here. So you understand, if you have to perform the operations on the dependent variable, the shift operation has the precedence. So if there is involved shift and reflection, so first we will shift the signal and then we will reflect. Or if there is involved the scaling and the shift, so first we will perform the shift and then we will scale, or any other, right? So remember that the shift operation has the precedence, right? So in order to obtain y of t, let's first obtain the x of okay, so let's first obtain x of 2t, right? So how to obtain the x of 2t, because we have done this scaling property is scaling operations in the previous lecture. So we understand that if the scaling parameter, right, so in a generalized way we write like this: x of a into t. So this is generalized expression for the scaling operation. If a is greater than 1, that means the resulting signal will be compressed form of the original signal, and how much compression will be there? They will be compressed by amount of a. If a is greater than 0 and less than 1, that means if a is positive value between 0 and 1, in that case the resulting signal will be stretched version of the original signal, right? So for example, if a equals to 1 by 2, in that case x of at will be the stretched version of the x of t by amount of this, right, 2. Now because we are given a equals to 2, so that means the x of 2t will be the compressed version of x of t, and that's also by amount of 2. So that means, because the original signal is, if I take the first part, which is from 0 to 2, so the original part is 0 to 2. If I scale it by a factor of 2, so that means it will be something like this. Okay, no effect on amplitude, so it will stay the same, but we are performing operations on this, so this will be 1. Okay, so 0 to 1, x of 2t will be 0 to 1, because why? We have compressed the signal by a factor of 2. So originally it was from 0 to 2, now it will be from 0 to 1. Now the second part, which is from 2 up to 4, this has amplitude of minus 2. We are doing no operation on amplitude, so it will stay the same, right? Because we are doing the operation on the t, right? So now because it has been scaled by a factor of 2, so now it will be compressed, and this is the compressed version of, right? So 2. So originally, if you look at the signal, it was from 0 to 4, because now we have compressed it from by a factor of 2. So now it will be from 0 to 2, and you can clearly observe that there is no effect on amplitude because we are not doing anything here. So this is again t-axis, right? So I hope this gives you idea. Now if I reflect the signal, right, so I will obtain the y of t, and y of t will be equal to sorry, y2 of t will be right, this is your y2 of t. So y2 of t can be obtained by time reversal of x2 of t, right? So x2 of t, this one, so that means if I put a mirror, you understand that on this side this whole signal is 0, right? So that means from 0 up to infinity this signal is 0. Again this signal is 0 from 2 up to positive infinity, right? So that means if I reflect it, so I put a mirror here, if I put a mirror here and I look from this side, right, the replica of this will be formed here. So 0 will be 0, okay, and because this is from 0 up to 1, this is 1, so it will be formed here, something like this, right? So this is your x of minus 2t. So this is minus 1, okay, and this is 0, this is your t-axis. So from 0 up to 1, originally it is 2, okay, from 0 up to 1 the value of the signal is 2, but if I reflect it, if I put a mirror here, I will get an image of this one this side. So now in the image it will look like from 0 up to minus 1 it will be 2, and again this thing from 1 up to 2 it will be formed here. So I hope you understand. So this will be something like, right, so this is your minus 1 and this will be your minus 2, okay, and the amplitude will stay the same, and this is minus 2 here, okay. So I hope this gives you the idea, and also you can differentiate or you can compare the operations performed on the dependent variable and operations performed on the independent variable, right? So if we perform operation on dependent variable, so something along this will change, like it is changed here, right? And if I perform operation along the t-axis, so the change will be in this direction, right? So like I scaled it, so you see it is originally it is here, but now it is the after the scaling by a factor of 2, this is compressed, and you see the signal moves in this direction, right? Again for reflection, original signal was here, now it is moved this way. So I hope this gives you the idea of what is how it's happening, right? So I think that's all for the operations on the signals, right, that include both the operation on independent variable and operation on the dependent variable. So you must go through the examples I have given, the problems I have given you, and if you have any confusion, we will meet in the live session and you can ask, okay. So that's all for the signals operations perform on the dependent and independent variable. So let's talk about let's start the new topic, that is elementary signals. So in this case we'll be talking about the exponential signals, sinusoidal signals, step, impulse and ramp signals, etc., both continuous and the discrete, right? So they are not only these signals not only occur frequently, but they also serve as building blocks from which we can construct many other useful signals. So their understanding is very important. And this part also about the part of the signals and system which we do in the which comprises the first part of your course. That is very important, because if you understand the signals and the systems, then that will be very easy for you to grasp the concepts of the following topics, which are the subsequent topics of the course that we'll do while doing the convolution sum or convolution integral, and also the Fourier series, Fourier transform, and the Laplace transform. So try to understand your concepts here. If you have any confusion, any problem you want to discuss, you must, because if you are good at this part, that will be very helpful for you to get the understanding of the remaining parts. So let's start the general form of a complex exponential signal, which can be which is written like this. So in the first part, we are talking about the continuous time case, and in the second part, we will discuss about the discrete time case, right? So this is the generalized expression for the complex exponential signal. So that is x of t equals to c, e, a, and t. So I hope you understand. Again, the t emphasizes that the independent variable is continuous, and it is also time, right? Or you can say, okay, because there's a one independent variable, so we say it's a one-dimensional signal, and because the independent variable is t, so that is time domain continuous time, right? So for the case of time domain discrete time, we write x of n. Again, c and a, they are constant, right? So you also understand the role of the t here, right? So depending upon the value of c and a, different characteristics of the signals, exponential signals can be, right? So in case 1, we consider that both c and a are real, right? So because we know a equals to sigma plus j omega naught. Now if a is real, that means j omega naught will be 0, right? So if j omega naught is 0, then we have a equals to sigma, a constant, real constant, right? And c is also constant, so the resulting signal will be a real exponential signal. Now whether this real exponential signal will be growing or decaying, right? Can anyone tell? So if we put the value of the c is real and a equals to sigma, right? So in that case, the expression will become x of t, which is this one, generalized is this one. Now it will be equal to this one, right? So I hope you can appreciate this one. So now because c is real, that means, and sigma is also real and constant, so that means it will be something exponential signal, right? Now it will be exponential signal, so it depends whether it will be growing or decaying on the value of the sigma. So if sigma is positive, in that case you understand it will be an exponentially growing signal, right? And example of the exponentially growing signals are the chain reactions in atomic explosion, or they can be in complex chemical reactions and so on, right? So I hope you understand why you get this waveform, because we assume that C is constant and sigma is and A is real. So in this case, if A is real, the real part of the A is sigma, and if sigma is positive, that means e power something positive. When you increase the t, with the increase of t, the value of this will increase exponentially, right? Because it's in exponent, right? So the resulting signal will be exponentially growing signal, right? At t equals to 0, the value of the signal will be c, okay? Because x of 0 means c, right? And e, this is sigma multiplied by 0. So anything multiplied by 0 will result into 0, and e power 0 or anything power 0 equals to 1. So that means this will be equal to c, right? So I hope you understand. So what if the c is negative? Okay, because this is plotted for c is positive, you can plot your graph by using the c equals to negative. Say you take c equals to, for example, minus 5 or minus 7, whatever you can take, right? And plot the resulting graph and see. Okay, so the second case will be when sigma is negative, right? So when sigma is negative, for example, sigma equals to, let's take it to be sigma equals to, for example, minus 5, right? So in that case, you can say x of t, let's okay, sigma equals to, and let's take c equals to, for example, 10. Okay, so then x of t will be equal to for example, 10 times the e power, for example, minus 5 into t, right? So you understand, at t equals to 0, it will have value of 10. At t equals to, for example, uh, 1, so e power minus 5. So you see, so I hope you understand, as the t increases, right? So the value of the signal will decrease because it's already there's 5 minus 5 with it, right? So when sigma is negative, that means it will be an exponentially decaying signal, right? Can you tell what will be the value of the signal at t equals to minus infinity, right? For example, t equals to minus infinity, right? Because t can have value from minus infinity up to infinity. So what will be the value of t at infinity? Sorry, what will be value of the signal when t is plus infinity, right? So when t is plus infinity, so that will be minus, right? So it will become minus infinity. You can write it like e power infinity. So what is the value of e power infinity? We can say that this is e power minus minus 5 into infinity at t equals to infinity, right? So if I replace infinity instead of in place of t, so I get this thing. So 5 multiplied by infinity will be e power minus infinity, and it would, I can write it like 1 over e power infinity. So this results into 0, right? So similarly, you can tell what will be the value of the signal when t is at infinity. So you understand, when sigma is negative, in that case the resulting exponential signal will be decaying, right? So it will be a decaying example signal. So example of decaying exponential signal is radioactive decay responses of RC circuits. I hope you have done this in your circuits course, and damped mechanical systems. Okay, so I think that's all for today, and the remaining uh, elementary signals, remaining parts of the complex exponential for discrete, for continuous and discrete time, we will discuss in the next lecture. So I hope you understand these things, and you should go thoroughly through the lectures, and you must also do the numerical problems that have been given here, so that you can develop a better understanding. I hope the course seems to you very simple and understanding, right? So if you understand these signals, I hope very well, or even you have just so idea of this, so the subsequent parts of the lecture of the course will be easy for you. But if you don't understand these, then that's very difficult for you to understand the subsequent topics. So if you don't understand, try to spend some time on it. You can discuss with your friends, and you can over and over again run this video, so that you have understanding. And if still you have problems, or if you understand, even then you should discuss this with with me in the live session with other students, right? So that will be quite helpful for you also. Okay, thanks. So see you in the next lecture.